So hello everyone, this is Akshay here, and as we already aware that previously we have discussed in a video the topological sorting, the DFS based approach, and then we have solved this question on GFG platform, and also following this we have solved a question of code schedule 2 on the lead code which has a problem number 210. So now in this video, as we discussed, that one of the more use case of the topological sorting is that to find the shortest distance from source to all the vertices in a direct acyclic graph, right? So before that, we need to cover that how a topological sort can be done using a DFS based approach as well, and then we'll move ahead with the other use case, right? So before starting that, if you're new to this channel, please like, share, and subscribe, and hit the bell icon to get the regular updates. So let us start ahead. So if you have not seen my previous video on the topological sorting, how it works, then please view it, review it, and come back to this video again. So because I will not be telling you what topological sort is, I will just tell you that how it is done in the DFS based manner. Correct. So let's say this is the graph. This is a direct acyclic graph. This is a direct acyclic graph. Directed because you have a directed edge and not so undirected edges, right? Okay, great. So let's say this is a directed graph, not a DAG. Let's assume that's a directed graph. Great. So this the color in the red represents the indexes in degree, right? In degrees. So what happens in the topological sort is that first we print those values or those node which has in degree equals to 0. So you can see 0 and 2 has the degree equals to 0. So that's what we have printed here. Then while we print the values of the in degree equals to 0, then at the same time we go to its neighbor and decrease the in degree value by 1, right? So since we have printed 0 and 1, this one will convert to 0 because 1 is a neighbor of 0, and 2 has two neighbors. Node 2 has two neighbors 3 and 4, so it will again be decreased by 1, so 1 and 1. Now you will see that in this current graph, the value, the node value, which is again having degree 0 and it is not printed in an answer, is 1, right? So that is why 1 is here. And then I will go again, 1 half the neighbor 3, so I will again reduce this in degree value by 1, and it will go. Now the node which has in degree value equals to 0 is 3, and that is why that is present in the answer. And similarly, since the neighbor of 3 is 4, we will again decrement the in degree value by 0, and that's the only node remaining also to be considered an answer. And since iska in degree 0 ho gaya tha, that is why that is a particular answer, right? And if you see, the 0 and 2 are printed simultaneously, like तो इसे हम 2 0 भी लिख सकते हैं, उसे कोई दिक्कत नहीं. But 1 3 and 4 were the individual answers for the iterations, right? So we cannot unjumble it. It should be in order 1 3 4, right? Great. I hope you are getting a good idea, and I hope if you have seen my previous video, I guess you would be pretty well understanding that how the topological sort is working. How can we do it is a DFS based approach. So what I'm saying is that let us start with the 0 here, right? Let us start with the 0 here and call the DFS, like recursively call a function for its neighbor. So let's say I'm calling for 0 now. So 0 will, what will do, if the neighbor exists, it will call recursively for the rest of its neighbor. I will say DFS of 1. Now it will check. Let me change the color first of all. DFS of 1. A DFS of 1, if there are neighbors available for 1, yes. So I will call for DFS of, let's say, 3. Now 3, it has the neighbor available? Yes, definitely it has. So it will call for DFS of 4, right? Now 4, does it have any more neighbors? So 4 does not have any more neighbors, right? So what we can do is we can maintain a stack, right? A stack structure, and we'll keep on pushing the nodes after the recursive call is done, right? So here in this case, what we can see is, so since 4 has none of the neighbors left, so what we will do, we will push it in the stack. We will push it in the stack, push 4, and 4 will come here. Similarly, 3 has no more level depth, so what it will do, it will push 3, and 3 will come here. Again, similarly, it will call for push of 1, and 1 will come here in the stack, and similarly for 0, I will say push of 0, and 0 will be here, correct? So now 0 has been, and in the meanwhile I'll keep on marking this node as visited as well, because I don't want to visit the same node twice, right? So we will have a visited array as well. It is 0 1 2 3 4, right? So we have visited which many nodes? 0 1 3 and 4 we have visited. So it would be true 3 and 4, right? Definitely there will be a for loop so that we can cover each and every node, because as you can clearly see, since we have made a recursive call for its neighbor, but you can clearly see that 2 still remain unvisited. That is why we need a for loop at the topmost part to iterate to all the nodes, which is to handle the case for the particular node which is left. Correct. So इसलिए ये call था equals to 0 के लिए, then I will make a call for I equals to 1, but as I can see that the 1 is already visited, so I will just skip this iteration. I will go for I equals to 2, and I can see this is false here, this is not visited. So I will call the DFS again. So I will call the DFS of 2. DFS is nothing but I'm saying the depth first because I'm using a recursive approach to visit elements in the graph. That is why I'm saying a DFS. So do not get confused by the terminologies. So DFS of 2. So if there are any neighbors left for 2, there are neighbors 3 and 4, but that is already visited. So we just need to skip here, right? Recursion is finished, and I will just say push 2, right? So this 2 would be, let me change the color. This 2 would be pushed due to which iteration? For I equals to 2. Then again for I equals to 3 would be got, but I can see that the node is already visited. I will skip again. I equals to 4. I will see the node is already visited. I will skip again. Correct? Now this stack is actually holding an answer of the topological sort. If you keep on popping out the elements till the stack is empty, you will get your answer. So if you keep on popping out, it will be 2, 0, 1, 3, and 4. And as I said, this 0 and 2, since this was the answer for the first iteration, right? जो भी आंसर एक इटरेशन में एक साथ आ रहा है, आप उसे इधर उधर करके लिख सकते हो, right? 0, 2 or 2, 0, that remains same. But you cannot change 1, 3, and 4 as I explained previous in the video, right? That is why 2, 0 can be interchangeable, and that can be a part of our answer, right? And 1, 3, 4, as you can see, this thing matches with this thing. And that's how the topological sort can be done using a DFS based algorithm. Great. Please pause this video here. I will mention the problem link of I'll mention the link of this problem in the description. Try doing this problem in the DFS approach. If you remember, we have discussed this particular problem in the BFS manner as well. So that's the let's say commented code here. You can get it in my DSA repository as well, or in the previous video link description. Please pause this video and now code this approach in the DFS manner, and then we'll move ahead with the use case of how we can find the shortest distance from a source node, or let's say a source node from all other nodes, right? To all other nodes, correct? Okay, so that's the code here. So so let me give you a very quick code walkthrough. So this is the DFS function which accepts the 2D adjacency list, right? Then we have a source node for which you need to iterate, for which you need to call recursive call for its neighbors. Then we have a stack. You know why? After the recursive call is finished, we need to add it in a stack, right? And a Boolean visited array. Let us get back to the topic. And so topological sort. First line is that we have made a Boolean visited array. Definitely, we don't need to visit the same node twice. We had a stack here, and then for each, and this is the for loop. That's the for loop I explained you here. Why it is necessary, right? This for loop. Why we have to write it, so that we cannot leave the nodes which is not getting handled by one recursive call, right? So that is why we need to iterate for each and every node. So if it is not visited, then only call the DFS call, right? Great, we have already discussed in the dry run again. So we have an answer array which will take the space of v nodes, right? Again, because that's the return type here is array, and we need to give an answer of the topological sort, right? So at the last, while all this thing is completed, all the recursive call is made, your answer is stored in your stack. So what we'll do, you will just keep on popping out the elements and store in the this answer array. Now if I just uncomment this line of st.peak, then definitely we'll see that this print statement will actually give you a topological sort ordering. So let us just verify that. So 3210 for this particular, that is saying that the answer is 3210. So can we verify that as well? So if you see at this graph, if you mark the in degree, right? If you mark the in degree, or let me just explain it in my board. So it was 1, this is 0, this is 3, and this is 2, correct? If you mark the in degree of these node values, it would be 0. In degrees is what? The number of edges coming towards it, right? And 0 has the in degree as 3. So definitely 0, no, not 0, 1, 2, and 3 can be printed at the same time, because all of these nodes have the in degree as 0. Now this can be interchanged. You can either print 2, 1, 3, you can print 3, 1, 2, anything, any order you can print, but it should be at the same time. एक साथ होने चाहिए, right? Now, since we have printed 1, then you will decrease the neighbor in degree value by 1, so it goes to 2. Since you have printed 2, again you will decrease the neighbor value, and neighbor is only 0. And again, since you have printed 3, the neighbor is again 0, decrement to 2. So now, in the updated graph, you can see that the 0 value will now be answer, because that's the in degree goes to 0, right? So 1, 2, 3, and 0, or you can say 3, 2, 1, 0. Everything makes sense, right? So 3, 2, 1, 0. And if you see in the question, like it says, find any topological sorting on that graph. So this line itself is saying that for one graph, many topological sorting, like जो भी array आ रहा है, like the array which we are getting from the topological sorting, उसके like variations हो सकते हैं, right? So that's why it is saying that if any variation is possible, just print it and I will take care of the rest. If your variation will be right, I will just print 1. Otherwise, I will say that your variation is wrong and I will say, and it will not print 1. It will print 0 for you, right? So let us just comment this line again. It's already 10 minutes, but it is okay. Let us compile and run this program. And then we'll hit the submit button and we'll do the C++ code again. So great, it has been done. Let us hit the submit button. While it is submitting, let us analyze the time complexity as well. So we are visiting each and every node. Correct. So please, yeah. I think you should think what is the time complexity for this code and then resume this video again. So yes, you were able to think it right. So for each and every vertex, we are visiting each their edges. And that is that we are visiting just once, right? So it may look like to you that we are, for each vertices, we are going to each and every edge, so V cross E. No, because we are visiting just once, so it would be V plus E, right? So time complexity will be V plus E, the same reason that we had in BFS and DFS. And what would be the space complexity? Space complexity will be O of V, because we are using a widgeted array of size V, that is the number of vertices given in the graph. And what else? Are we using any more space? No, this answer we have used because the return type was this. Yes, we are using a stack and a boolean widgeted array of V space. So again, the space complexity will be O of V. If we just verify the expected one, it is V plus V and V. Great. Let us see the C++ code now. Okay, here goes the C++ code. I don't think a code walkthrough is required. So let me just scroll it down for you. It's the same thing we have written. It's the same thing that we written in the Java. Just the syntaxes has been changed. Just the declaration of data structure has been changed, and all the logic remains same. So yes, let us hit the submit button for this code as well. And one thing that you will get the link of all the source codes present in the description or in my DSL repository. I'll mention the link of this problem as well as the source code. And yes, we are done with the DFS based of our topological sorting. And I hope you have gotten a good idea that how we can solve this question using a DFS based approach, right? So yes. So great. If you're getting help from this channel, it's a free channel for all of you guys. And one thing more is free for you is that you can hit my subscribe button, and I also get motivated to continue the playlist forever. And yes, let us end this video here, and then we'll meet again in the next video. That is the use case of the topological sorting. That is the finding the shortest distance from the source node to all the vertices to all the other vertices, right? Okay. Let us meet in the next video. Till then, keep learning, keep growing. Bye bye, and take care, guys.